I want to talk about electrodynamics. So that's what happened. So you kindly pay attention. If you don't understand anything, humbly let me know so that I take my time and take you through it. That is all. That is all. Let me put this. Let me add them so that we continue. So we've first of all, let me wish you a prosperous month. We are in a new month, so God see all of us through, just as He did for us all these months we've been home. Let's also not forget to take good care of ourselves. That one too is a necessity. So let's humbly make sure we take good care of ourselves. Oh. Today we are doing magnetic field, electrodynamics. And I think we started the last time, but I would have to brush through because we have some new members around. We are going to consider the basic concepts under electrodynamics or magnetic field. We are going to define what magnetic field itself is. We are going to talk about the magnetic lines of force. We are also going to talk about the direction of magnetic field. We spoke about all these last week. And for the sake of those who couldn't make it, we are going to talk about it today. We're also going to talk about the types of magnetic field we have. And from there, we move straight into the characteristics of the various types of magnetic fields. Then from there, we move straight into magnetic flux and flux density. We solve questions and right. Then we do we talk about force on the current conductor, where we are going to consider the Fleming's left-hand rule. Then I think we continue. So first of all, the other time we studied that magnetic field is the region of magnetic fields is the region around the magnets or a current conductor in which a magnetic force is experienced. And so we consider that a magnetic field is an area around area or a region around a magnet or a current conductor in which a magnetic force is experienced. So the area where a magnetic force is experienced is what we term as magnetic field. And we say that it can also be defined as a space or a region in which a moving charge particle experiences a force. And so in which a moving charge particle also experiences force. And so the area where the magnetic influence or magnetic force is felt most is what we term as a magnetic field. And so that is it. Now from there, we said that these magnetic fields, because we can't see them, they are normally represented by lines. And these lines are what we term as magnetic lines of force. And the magnetic lines of force are imaginary lines or lines drawn to represent a magnetic field in magnitude and direction. And so because we don't see this field, normally we draw lines or we use lines to represent these fields and both their magnitude. When we say magnitude, the size of the field and the direction. I mean the direction in which the field takes or the path in which the field takes. And so we are saying that magnetic lines of force are these lines drawn to represent a magnetic field in magnitude and direction. And this is known as magnetic field lines of force. In other words, magnetic flux. So anytime I say magnetic flux, then you know I'm talking about magnetic lines of force. That is it. And so we first consider the definition of magnetic field. Magnetic field. Magnetic field. We are talking about magnetic lines of force. So we have magnetic lines of force. Magnetic lines of force. Now we are going to talk about direction of a magnetic field. We said that the magnetic field takes a direction, and these directions are normally represented by the lines, and the arrows accompanying it, and the arrows show the direction in which or the path in which the magnetic field takes. Magnetic field. So we are saying that now is the direction in which a small north pole tends to move when placed at a point. So the direction of a magnetic field is the direction in which a small north pole tends to move when placed at a point. You study, you realized last week I said the magnet has two sides. In our previous studies, the magnet has two poles, the north and the south pole. And I said that normally the field moves from the north to the south. It doesn't move from the south to the north. It normally moves from the north to the south. And so basically that's what we're trying to this mean. So that is the direction. The direction normally moves from the north pole to the south pole in every magnet. That is it. Now from there we are going to consider the types of magnetic fields we have. We have basically two main types of magnetic field. We have two main types of magnetic field. The first one is types of magnetic field. The first one is uniform magnetic field. The first one is uniform magnetic field. So we have the uniform magnetic field, and we have the non-uniform magnetic field. So that is it. Now, what are the characteristics that defines a uniform magnetic field, and that which defines a non-uniform magnetic field? Now, so we are going to consider when we say a uniform magnetic field or a magnetic field is uniform, what are some properties or features or characteristics that constitute or that defines a uniform magnetic field and that defines a non-uniform magnetic field? So we are going to consider the first one. So we are going to consider the characteristics of a uniform magnetic field. So we are saying that when you have a uniform magnetic field, the magnetic lines of force are parallel to each other. So in a uniform magnetic field, the magnetic lines of force or the magnetic flux are normally parallel to each other. Now, when we say something are parallel, we mean that they are equally spaced and they move either the same direction or this, but they never meet. And so they are parallel. Basically, here we are going to say they move in the same direction because we know it moves from north to south. So that is it. And the lines of force are equally spaced. Yes, I just said it. And the magnetic field intensity, also known as the flux density. When we get to the flux density, I explain it. So magnetic field intensity, we mean that the intensity or the strength of the magnetic field is the same in every, or it is the same or constant at everywhere. So at every point you find yourself in that field, the magnetic field intensity is the same. It is the same. That is it. The magnetic lines of force have the same direction, and they also have the same direction. I've already said this. They have the same direction. Now, examples of these uniform magnetic fields are the field between the north and south poles of a large permanent magnet. So normally the field between the north and the south poles of a large permanent magnet is what we term as a typical example of what we call a uniform magnetic field. And so going to the characteristics, I said that the magnetic lines of force are parallel to each other. I said that the lines of force are equally spaced. I also said that the lines of force also move in the same direction. And I also said that the intensity of the magnetic field is equal or the same or constant at everywhere, at every place in the magnetic field. That's what I said. And I said a typical example is the force that is normally, or the magnetic force between two permanent bar magnets. And so the other day, I think I drew it. And so the field between two permanent bar magnets is what we call field between the north and south pole of a large bar magnet. So the field between the north and south pole of a large bar magnet, yeah, not two permanents, of a large permanent bar magnet. That is it. Now, another example is a magnetic field inside a solenoid. When we're talking about the magnetization of a magnetic material, we spoke about magnetization by electrical method or something. And so the magnetic field that is generated inside the solenoid, which is when we see the solenoid, we're talking about the coil of the wire. That magnetic field inside, not outside, inside is what we term as one example of a uniform magnetic field. Now, another example is the magnetic field between the poles of a U-shaped magnet. Between the poles of a U-shaped magnet, you know, some of the magnets take the form or take the shape of a U, and so the magnetic field between the north and the south is one example of a uniform magnetic field. And so we can first write that one example of the uniform distance is the field between field between the north and south. North and south of permanent bar magnet. We said that, and we also said that field, the magnetic field, you add a magnetic field between field inside a solenoid. Solenoid. We said that, and we also said that three fields between.
What are you looking for?
Field between a U-shaped magnet. A U-shaped magnet. That is it. Now let's also consider non-uniform. You know that the non-uniform alone defines how it's going to look like or how the fields are. Now, characteristics of a non-uniform magnetic field. We are seeing that the magnetic fields or the magnetic lines of force are not parallel to each other. So here the magnetic lines of force, they are not parallel to each other. That's number one. They can be represented by curved lines which are not equally spaced. So they are normally represented by curved lines which are not equally spaced. And so one is they are not parallel. They can be represented by curved lines which are not equally spaced. Now, a moving charged particle in a field experiences available force at different points in their field. Because of the nature of it, they do not experience equal field or equal intensity of force at every point. At this point, they may experience a higher one, especially when they are near in the poles. They experience a higher what we call magnetic field intensity. Now, when they are moving away from the poles, normally the intensity of the field reduces based on the nature of how it is. Now, the magnetic flux density of the field intensity varies from point to point. That's what I just explained. Now, example of the non-uniform magnetic field are the magnetic field around a bar magnet. So the magnetic field around the bar magnet is one example. Magnetic field field around a bar magnet. Now, number two, magnetic field around a solenoid. Magnetic field, so field around a solenoid. This time not inside, around a solenoid. Around a solenoid. So these are two examples of bar magnets around or outside the solenoid, whichever way. That's it. So these are the two main examples of an uniform magnetic field. Any question? Okay, so let's move straight. Now, from here we are going to talk about what do you call it? Magnetic flux density. Magnetic field lines. Oh, sorry, magnetic flux density. Your magnetic flux and flux density. We are going to consider magnetic flux and flux density. So there are two different things. So we are first going to consider magnetic flux density. Magnetic flux density. Flux density. Now it is denoted by B. When I say denoted, I know you understand. It is represented by B. And so anytime we see B, you know you are talking about magnetic flux density and the magnetism. Now when we say flux density, we already know that magnetic flux has to do with the lines representing the magnetic field. Now when we say magnetic flux density, you know basically when we talk of density, we are talking about a certain volume all over, a certain mass all over volume. I think so, yes. In this case, we are talking about a certain space and or area and the number of lines or number of lines in that area. Let me put it that way. And so we are saying that a magnetic flux density of a magnetic field is the number of lines of flux. So the number of lines of flux or the number of flux per unit area, per unit cross-sectional area, which is perpendicular to the field. So we are trying to say that if you have an area where your magnet is. We are talking about the number of lines in that area, or the number of lines per unit area. So for instance, the other day I said it, if you have two equal classes at McGee's, I want to talk about the strength or the magnetic flux density, or the flux density, or the density of the two class. You are first going to consider the area of the class. So if it is the same this in the area, then now we are going to talk about, in this case, the number of human beings in each class. That will help us determine the density of the class. So for instance, if you have more people in one class than the other, but the same area or the same size of class, then you are saying that one class will be denser than the other. That's basically what it means. So the magnetic flux density is the number of lines of flux per unit cross-sectional area, which is perpendicular to the field, So therefore, we can mathematically define it as B is equal to, there's this sign. It is, I call it psi. I don't know how I'm going to draw it so that you see it, but I'll try. It is more or less like kill. It looks like a kill. I don't know if you've seen that sign. It looks like a kill. All over area. So mathematically, we are saying that magnetic field flux density is the number of lines. So the number of lines constitute that of the Q I'm saying here. It's a psi in a distance because of the machine. I don't know how I'm going to listen, but I'll write it. I'll draw it. This psi all over area. So the number of this per unit area. That's what it means. So then now we can say that magnetic flux. So this one becomes the magnetic flux. When we say magnetic flux, we're talking about the magnetic lines. Now the lines in the area now becomes the density. So before we can be able to get the density, you are supposed to get a certain area or a certain cross-sectional area. Number one, we are going to consider the number of lines drawn or represented in that area. And so that constitutes the magnetic flux density. I hope you are getting it. That is it. So so in that case, we can say that K. This is equal to, mathematically we can say this is equal to BA, right? B times A. So we can say that magnetic flux, which is the magnetic lines of force, which are drawn to represent a magnetic field, can also be calculated as the magnetic flux density times the area. That will give us this. Now let's consider the unit. We are saying that the SI unit for magnetic flux density is Tesla. So SI unit for magnetic flux density, which is B, is Tesla. You know, now Tesla is a car. It's the name of a car. Someone have named that after a car. You can go and check. It was made by Elon Musk or something. Yes, he's one of the richest in the world. He's into space and all those things. So Tesla, and the Tesla is capital T, and that of the magnetic flux is given by, or is equal to, what you call, measured in magnetic flux is measured in Weber. WEBER, and it is also denoted by Weber. That is it. So that is it. So 1 Tesla. You bear with me that if you want to find for, what do you call it? We want to find for the derived unit of B, which is the magnetic flux density. You bear with me that it will be Weber. So SI unit for T will be, SI unit for T, for B, sorry, will be, we can also, let me write it here so that looking at the formula, we can see that T is also equal to, is equivalent to Weber per meter square slash M raised to the power 2. Or, I hope you agree with me, because this is measured in Weber and area is measured in meter square. So then we can see that the SI unit for this is this. Yeah, Ruben, talk to me. Ruben,
So, sir, is the magnetic flux density and the magnetic flux, are they fundamental units or base unit?
is it this one? Is it the Tesla and the Weber? Are you talking about the Tesla,
Yes.
the Tesla and the Weber? Yeah, the Tesla and the Weber. Let's say they are fundamental or base
Yes,
units.
sir.
And this one is the derived unit. The derived unit of this. The derived unit of this is Weber per meter square. That's if you have to use the formulas to there's the SI units to derive the unit for B. That's what it is. So this one becomes the derived unit, and this will become maybe the base, the fundamental unit we already know. And normally, you know, these units are normally named after those people who, the scientists who were able to propound these theories or who made experiments to find out all these things. They normally name them after that. And so that is it. So it is likely that Tesla is the name of one of the scientists, and Weber too can be a name of one of the scientists who played a lot of role in bringing all these things, this theory to fruition. So let me use this thing to draw the so the Q I was the psi I was talking about is something like this. When you see something like this, or in other words, you can also something like this. There is it. This is supposed to be. This is, I don't know if you've seen it before. This is supposed to be, but for the sake of this, let's use the kill. But just take note that it's psi, not kill. No. So that is it. So that's it. So we can say that we can therefore see that 1 Tesla is equal to 1 Weber per meter square. That's what we can humbly say that. Now, if the normal to the surface, so if the normal to the surface A makes an angle with the direction of the flux, then the magnetic flux psi through the area is given by. So for instance, if the normal to the surface A to the surface, the area you are talking about, which is the area where the magnetic flux is drawn, if it makes an angle, if it makes an angle in the direction of the flux, then we can see that the magnetic flux now will be considered as B can now be considered as B. We can see that the flux rather, sorry, K can now be considered as BA cos theta. This is theta, not 0. This is theta. So that's it. So this is equal to BA cos theta. That is when an angle is this thing. When an angle is considered.
Hey, the car is nice, so hey,
when an angle is considered, that is it. So we have psi is equal to BA cos theta. That's when an angle is made, considering the directions and so on and so forth, and an angle is made. And we are seeing that the flux now becomes BA cos theta. So these are 1 or 2 things we have to consider. Let's solve some 1 or 2 questions. Calculate the magnetic flux through a coil. Calculate the magnetic flux. I'm reading, so you write. Calculate the magnetic flux through a coil of area 0.4 meter square. Calculate the magnetic flux through a coil of area 0.4 meter square. Through a coil of area 0.4 meter square. Line normal to a field of flux density 0.5 T. Calculate the magnetic flux through a coil of area 0.4 meter square, line normal to the field of flux density 0.5 T. Calculate the magnetic flux density through a coil of area 0.4 meter square. Line normal to the field of flux density 0.5 T. So
0.2 Weber.
okay, you had 0.2 Weber. Okay, correct. Who else? Okay, let's do. Am I recording? Okay, I'm recording. So let's do another one. Please, who else had the 0.2 Weber? So the answer is 0.2 Weber using the formula.
Sir.
Number 2.
0.2 Weber.
Oh, God bless you. I miss you, pa. That's
I missed
I miss you. Now let's take the second one. Calculate the magnetic flux. Calculate the magnetic flux through a square coil. Or coil. COIL. Through a square coil of size 10 cm. Set. What it planes at 60 degrees. To the field of flux density 1600 Tesla or 1600 Tesla, 1600 Tesla. Let me reiterate. Calculate the magnetic flux through a square coil of size 10 cm set. What it plane at
how many?
What it plane at 60 degrees to a field of flux density 1600 T. So let's do it.
So the magnetic flux density.
I'll calculate the magnetic flux through
Sir, please.
talk to me. The magnetic flux density is 1600 Tesla.
Sir, please, 80 Weber.
Is that 80?
80 Weber.
Oh no. Yeah, correct, but you're having a problem with the you convert you have to convert the distance to decimeters. Have you seen that?
Sir.
Yeah. Talk to me, Tina.
Please, I had 8 Weber.
You had what? 8?
Yes.
So also 80 Weber.
The 8 is correct. Those who are the 80, the issue is you are not you forgotten that the 10 cm I gave you is in centimeters. So you are supposed to convert to meters.
Okay.
So kindly convert.
Sir, please, 800 Weber.
800. Wow. Please check again. Don't forget that there's cost 60 and all those things. And one issue is don't just multiply by this. No. Just take note that you are talking about the area is square. So before you can be able to find for area, it's supposed to be length times length of the square is length times length or length times breadth. Anyhow you are going to see it. And so if you convert 110 and you know area, they have equal sides. So you would have to, before you can find the area, you have to multiply the 10 by 10. Let me put it that way. That will give you 100. And when it gives you 100, then you convert the 100 to meters. Then now you can multiply, you can do your arithmetic. Are you getting it?
Yes, sir.
On this thing, and you join us so that we complete. We do our next. Oh, sorry.
Say 8 Weber.
Correct.
So I had 8 Weber.
Okay, correct. Correcto. Let me see if I can get you someone there. That I want us to start a new this. I want the lesson to end so that we can start again. So that is it, and now we are going to consider the force on a current conductor. The force on a current conductor. Now you bear with me. Now when current passes through a wire which is near a magnet, the wire is seen to move around the magnet in a particular direction. This means that when current is established in what do you call it, in a wire, it causes or it creates something called a magnetic field. So now when that magnetic field, or when that current passing through the wire is placed near what do you call it, a magnet, because the magnet is also already it's also a magnet, it tends to move around the magnet in a particular direction. That means they tend to have some mechanism. Now, when the direction of the current is reversed, definitely the direction of the motion of the wire is seen to be reversed too. The direction of the motion of the wire is also seen to reverse. Now, when the current is increased, the wire moves faster. That means when the current is increased, then now we can say that the magnetic field created by the current also increases. So as a result, the wire moves faster. Now there's a force acting. So in this case, we can now establish that there's a force acting on a current conductor in a magnetic field. That's what we just wanted to establish. That is why you bear with me that when we're talking about the magnetization, we said that one other method we can magnetize a magnetic material is placing what do you call it, a nail or a magnetic material in a coil, or wounding a coil around a magnetic material and connecting it to a direct current. So in this case, what it meant is that when current passes through a coil, it creates that magnetic field. So when you bring another magnet near the wire, you realize that the wire tends to move in the direction of this, and that is, it's either try to attract the other magnet because there's a magnetic field established in that, what do you call it, in that coil of wire because of the current passing through. That's what it means. And so we are going to talk about the force on the current conductor. When the class comes back, then we can progress. Then we talk about the Fleming's left-hand rule. We do some mathematical arithmetic there, the mathematical representation of the Fleming's left-hand rule. Then I think I want us to finish everything. Then maybe if you have time, we do talk on a rectangular coil in uniform field. Then yeah, this thing. That is it. The class will end very soon. Then immediately ends, you join and please.